Today we're going to deep dive into consensus mechanisms. So let's start. We will begin by exploring peer-to-peer networks and then compare them to the client-server systems. We will talk about the Byzantine Agreement and the concept of consensus and its mechanisms. Finally, we will look at the proof-of-work consensus algorithm. Blockchain technology utilizes peer-to-peer network where all nodes are on the same level and can communicate directly with each other. The network doesn't have a central authority or a server. Each node is both a client and a server, allowing them to share resources and data. This system enables effective distribution, collaboration, and scalability. A client-server network, on the other hand, splits clients and servers, with clients requesting resources or services from servers that respond, having a clear distinction between them. There are differences in architecture between P2P networks and client-server networks. P2P networks are decentralized, meaning that there is no central authority or server controlling the network. Instead, each node contributes resources and participates in sharing data. Meanwhile, client-server networks are centralized, with servers acting as a central points of control, managing resources and serving clients' requests. In terms of scalability, P2P networks are generally more scalable because each new node that joins the network contributes to its overall capacity and resources. However, scalability in client-server networks depends on the capacity of the central service. Adding more clients may increase the load on servers, potentially leading to scalability challenges. As for security, P2P networks may be more secure because there is no central point of control that could be targeted by hackers. However, P2P networks can also be more vulnerable since each peer is responsible for securing its own data and resources. In terms of efficiency, P2P networks may be less efficient since data and resources are distributed across multiple peers and may require multiple hops to reach their destination. On the other hand, client-server networks can be efficient since all data and resources are stored and managed on a central server. Although P2P networks have their advantages as a decentralized network, all nodes must follow the same rules to be effective. Before discussing these rules, let's start with a simple example of a Byzantine agreement. The Byzantine Agreement is a problem that shows how hard it can be to agree in a group when some people might not be trustworthy. It's like when some generals are planning a joint attack, but some of them might be disloyal and send messages that confuse everyone. This is a problem for computer algorithms that try to reach agreement between different parts of a system. To solve this problem, these algorithms have to find a way to agree on one thing, even if some parts of the system cannot be trusted. In order to proceed with a coordinated attack, all members must unanimously agree to attack. Similarly, if a decision is to retreat, all members must agree to do so. However, the presence of a traitor who disagrees with the other generals can cause confusion and disrupt the system. Therefore, it is crucial that every participant reaches a consensus before taking action. This example highlights the importance of a consensus algorithm. In a decentralized system like blockchain, where there is no central authority, consensus algorithms are necessary to ensure that all nodes agree on the state of network. These algorithms provide rules and protocols that guide nodes in reaching an agreement, despite the presence of malicious participants. To evaluate the effectiveness of the consensus algorithm, there are several attributes that need to be considered, including fault tolerance, scalability, security, and decentralization. Fault tolerance refers to the algorithm's ability to tolerate certain faulty nodes, which helps to ensure that the system remains operational and secure. Decentralization is important because it allows multiple nodes to participate in the decision-making process, which helps to avoid the risk of a single point of failure. Scalability is another important attribute as it refers to the algorithm's ability to handle an increase in the number of nodes or transactions, while still reaching consensus efficiently as the size of the network grows. Finally, a secure consensus algorithm uses cryptographic techniques to protect against attacks or other threats, which helps to ensure that transactions are secure and cannot be altered. There are different consensus algorithms, and one of them is a proof-of-work consensus algorithm. Proof-of-work consensus algorithm is a method used by Bitcoin to achieve distributed consensus in a distributed system, ensuring all nodes agree on the validity of transactions and the order of the blocks. The working principle of the following consensus is that it is necessary to mine a block. So nodes or computers start a competition to solve a mathematical puzzle. In this puzzle-solving problem, a hash function is employed. A hash function is a highly complex and unpredictable mathematical function utilized to authenticate the stored transactions within the blockchain networks. A miner tries to calculate the hash. It tries to achieve a particular nonce value so that the hash can fulfill predefined terms and conditions. By adjusting these conditions, the network can achieve high flexibility and scalability. In the proof-of-work system, each node in the network calculates the hash value of the block header. When a node identifies the target value, it broadcasts a new block to the network, and all the other nodes verify the correctness of the hash value. Once the block is confirmed by all nodes, it can be added to the network and miner obtains a reward. Well, in order to control the rate of block production, miners are required to solve a puzzle for every block they create. The puzzle involves ensuring that the block hash meets a certain format requirement. For instance, miners must obtain a hash value with a certain number of digits being 0. To achieve this, miner must solve the puzzle to generate a new block. This mechanism effectively prevents malicious miners from producing blocks consecutively. In the Model 1, we discussed the various components that make up a block, including version, previous hash block, timestamp, difficulty, nonce, and Merkle tree. All of these components are represented in the block hash, but the only parameter that can be found is the nonce. The rest of the block parameters are pulled from the network itself. The goal is to find a nonce that will yield a specific number of zeros, and once it's found, the block can be mined. This block hash does not start with zeros as it's supposed to be, so it is necessary to increment nonce by 1. This block hash does not start with zeros as well, so we are continuing to increment nonce by 1. Finally, this block hash starts from 6 zeros. So the block is mined and the miner gets the reward for it. Thank you for watching and see you on the next video about the different types of consensus mechanisms.